Welcome, ladies and gentlemen, to another riveting episode of Dave Does Math from Home. I tried really hard to record this video yesterday, but the camera died, and then the spare battery died in the middle of both of those. So we're picking up where we left off yesterday with implicit differentiation. This is part 4 of our series on implicit differentiation. The things we still need to talk about are the chain rule, the difference between my method and the book's method, and logarithms. So let's get started on the chain rule. If we do something like the sine of y to the fourth minus xy equals 7. This is an implicit function with a composite function as part of it. So when we start doing this one implicitly, if we want to find dy dx, for this problem we're only just going to find the derivative. I don't need the equation of a tangent line. Getting the equation of a tangent line pretty much means that you have to know the coordinates of a point that's on this function, and I don't. I could figure it out if I had to, I just don't want to. So I just want the derivative. We're going to do that implicitly, piece by piece. We'll start with this piece. This is a chain rule piece. The derivative of sine is cosine of what's inside. The derivative of what's inside is 4y cubed. The derivative of what's inside that is dy. So this is a chain rule thing with 3 pieces. This is a product rule. Derivative of xy is x dy plus y dx. Derivative of 7 is 0. So we can check. We have 3 pieces here. Here's a piece, there's a piece, there's a piece. All of these pieces have exactly 1 d in them. That's our easy check to see if we've done the derivatives right. So we're good there. We can start consolidating pieces. I like to put all of my dy's on the left and all of my dx's on the other side. So I have a dy times this whole business, cosine of y to the fourth times 4y cubed. This is a dy piece, so I'm going to do minus x. This negative sign needs to distribute, so this is actually minus y dx, which means I need to add it to both sides. So I'll get y dx on the right as well. And this is now completely separated. All my dy's over here, all my dx's over there. We're good. Now I just need to do some division. I'll divide both sides by dx, so that cancels, and this becomes what I want. And I'll divide both sides by this giant set of brackets. Cosine y to the fourth times 4y cubed minus x. I'm not going to write it. You know what's in the brackets. It's being divided there. Cancels here. dy dx equals y over cosine y to the fourth times 4y cubed minus x. And that's the derivative. So you can see the chain rule works exactly as you'd expect it to. There's no sneakiness or surprises here. It's still the same old chain rule. You just, part of all of this process with implicit differentiation is you do a chain rule piece with just a dy or just a dx on everything. So if that happens to be the last piece of a longer chain, cool. That's why it's called the chain rule. If that's just one small piece of a small thing, that's fine too. You have to include it anyway. That's the chain rule with implicit differentiation. Next on the agenda is a discussion of the difference between my technique and the book's technique. For that, I'll do something pretty simple. X squared y minus 2x equals 3y. Here's an implicit function. I'm going to write it twice. So that we can do it once with my technique and once using the book's technique, and you can see what you like better. I mentioned in an earlier video that this technique that I'm showing you with you dx's and dy's is not the official book endorsed technique. It's a little different from that. So I want to show you the book's technique here, so that if you find yourself using the help me solve this button or the show me an example button, the text that the book gives you is somewhat recognizable. It's not the first time you've ever seen it. And also, just in case, if you like the book's techniques better, then that's what you should do. Use whatever technique makes the most sense and is the easiest for you. For me, I generally prefer my technique. I think that it makes more sense, and also I think it's going to make future sections much more clear. Like when we do related rates in a couple weeks here, I think related rates is more clear if you practice this way. And in Calc 2, when we start doing a lot of integrals, and especially when we start doing differential equations by separation of variables, I think that my technique makes those sections much more accessible. That's my pitch for it. Again, you don't have to use it. Use whatever you're comfortable with. Use whatever makes the most sense. Do not feel pressured one way or another. So, I'm going to take derivatives of both of these things, first with my technique, then with the book's technique. We'll see what the differences are. This piece starts out as a product. So we need the first times the derivative of the second plus the second times the derivative of the first. The derivative of the first is 2x dx. This is all coming from the chain rule and the product rule. The 2x is going to turn into a negative 2 dx, and this 3y is going to turn into a 3 dy. So this is the derivative step using the Dave technique. Using the book's technique, this is going to look sort of similar. We still have a product and we still have to deal with that first, and we shall. So the product rule says that we should do the first times the derivative of the second. According to the book, the derivative of y is dy dx. To this we have to add the second times the derivative of the first. According to the book, the derivative of this is just 2x. Then we'll add negative 2 is the derivative of this, and the derivative of 3y is 3 dy dx. So the basic difference here is, in my technique, I attach a single d to every single piece every time I take a derivative. Here I took the derivative of y, so I attach a dy. Here I took the derivative of an x, so I attach a dx. This is just what the chain rule has us do. In the book's technique, you sort of assume that y is always the dependent variable, and so its derivative is dy dx, the derivative of y with respect to x, since you assume that x is independent. And then every time you take the derivative of a y piece, you add this dy dx, like the full entire derivative term. And every time you take the derivative of an x piece, you add nothing, because x is assumed to be independent. Mathematically, these are the same. If you take this equation that I created, and if you divide the entire equation right now by dx, these things would cancel, and these things would turn into dy over dx. It would become exactly like this. And in fairness, dividing the entire equation by dx is something that we are going to do eventually I just do it after I have these things isolated. So they are equivalent, they just look different. I think this one looks nicer. This is more accessible to me. If you prefer to do it this way, with dy dx's as the derivatives here, and nothing as the derivative here, you could do it that way as well. Doesn't make a huge difference to me. Whatever you're more comfortable with. If you like, you can finish these. I'm going to leave them here. I think I've illustrated the difference, and finishing them at this point is just a matter of algebra. I'll do this. There's this trick that math books all do. They leave things as an exercise for the reader. So I'm going to do that, because I still need to talk about natural logs. I got a question this morning in class saying, why am I doing section 3.8 and 3.9 out of order? And I said, the reason is 3.9 is our section on natural logs. We did that well before this video. And we did it before this video because I think natural logs are a basic kind of function that you should have access to in the section of the class that is about basic derivatives. So I put it in with the other stuff. Implicit differentiation is, in my mind, a very advanced derivative technique. But if you want to take the derivative of a natural log without using graphs, when we did it in our video, we used the graphs. I just created a graph of a natural log and I was like, look at the slopes. If you graph the slopes, it makes a hyperbola. That's 1 over x. So we used a very graphical argument to come up with that derivative. If you want to use an analytic argument to come up with that derivative, you need to use implicit differentiation. So I want to show you that real quick, just as a wrap up to this whole section. This is one of the neat practical uses of implicit differentiation. If you start with this function, y equals natural log x, and you want to know the derivative of this, and we'll assume for now that we don't already know what the derivative is. We're trying to discover the derivative of this, and we have no idea how to handle a natural log. That's okay, because we can do this. We can rewrite this function like this. We can just say e to the y is x, because these things are equivalent. If y is the natural log of x, then x is the exponential of y. That's what this relationship means. And we do know the derivative of e to the y. So this is something that we can take a derivative of using implicit differentiation. And this is why the section comes after 3.8 in the textbook, because they think you need implicit differentiation to do this. So the derivative here, e to the y turns into e to the y dy, x turns into 1 dx. So I need to divide everything by dx. So that cancels. I need to get rid of this e to the y. So I'll put an e to the y over there. So I have dy dx, the derivative of my function, equals 1 over e to the y. Which is true and it's nice, but it's also got a bit of a problem. When we started this, we had an explicit function, y equals the natural log of x. It would be nice if, when we got a derivative, that derivative was also explicit. That is, we had derivative of y equals some function of x's. We don't really want any y's to be on the right-hand side of this equation. It would be nice if it was all x's, because that sort of preserves this dependent-independent variable relationship where you can just pick an x value, plug it in here to get a y value, or just plug it in here to get a slope value. We don't want to have to plug a y value into this, because then you're sort of muddling which one's dependent and which one's independent, or which one you just pick values for and plug in. So we want to turn this back into something of x's. Fortunately, we have a very clear relationship with which to do that. So dy over dx equals instead of calling this 1 over e to the x, or sorry, 1 over e to the y, I'm going to call it 1 over x, since that's what e to the y is equal to. And this is the analytical derivation of derivatives of natural logs. That'll do it for this video. Hopefully it wasn't too disconnected from the other three I did back to back to back. Stay tuned. We're going to talk immediately about section 3.10. It'll be a good time.